So any questions? No questions? Okay, so yeah, so we sort of want to conclude like the pre-ADS-CFT part of our course today. And so what I'll talk about is sort of a continuation of what we were talking about regarding page curve. So, and sort of a natural continuation of it, which is called the Hayden-Preskill called a protocol, sometimes experiment, thought experiment, whatever. Okay, so Hayden-Preskill protocol. So what it basically tells you is how fast can you extract information from the black hole. You know, once you're inside, once black holes are formed, how much information is there. You know that it is made of some initial state which has some information, and what we found out was that information starts coming out basically only after the page time, right? So until then, the radiation is maximally entangled with the black hole. So and so the late radiation is entangled with early radiation, but early radiation is entangled with what was there in the black hole. Okay, so that's the rough idea. So what Hayden-Preskill protocol is basically about is that you want to, so first we have to kind of define what we mean by extracting quantum information. So we'll say some words very roughly. The idea would be that let's look at some example of what it means to say that. So let's say you can do this. So I'll tell you why. I mean, this may sound kind of disconnected and abstract. So I'm trying to follow Harlow here. But even though the second half I'm actually following the Hayden-Preskill paper. So, but let's start with Harlow. So the point is that let's say you can do this, then this is what we mean. So if you can do, if an operation can do this, then we say that we can transfer. This is called transfer of quantum information. Okay, so quantum information basically is about the ability to copy states. Okay, it is not the same thing as, so that's essentially the difference between classical information and quantum information. So if you want to characterize a state using classical information, you would basically have to talk about the coefficients in some basis and the coefficients of that in some basis. Okay, that's a huge number of complex numbers. Okay, typically if the state is like in a huge dimensional Hilbert space, it's classically it's a huge amount of information. So, but instead, if you think of it in terms of the state itself, so when we say that we can extract quantum information, what we mean is that we can somehow or the other copy a state into, from some Hilbert space to some other Hilbert space. Okay, so but of course, as I said last time, you cannot copy, you cannot just clone quantum information. What is that? What that basically means that, let's say you had an initial state like this, which was phi and some state. So you cannot make it go to this. Okay, so that's what this is. This is not possible. This is essentially what cloning means. Okay, so cloning is not possible. This is trivial to prove. You can check this is an exercise. You can look it up on Wikipedia if you don't know what the proof is. But so the point is that if you roughly speaking, that's the reason why we phrased transfer of quantum information in this way. Okay, so we are kind of exchanging. We had some state here, and we are putting, you're going from here to here, but you have lost some information. Like it is roughly like there is a conservation of quantum information, if you like. Okay, so this is no cloning. So the point is that if you are talking about quantum mechanical states, transferring information is basically your ability to copy states. That's what information means. Copy means copy with some price. Okay, so if you copy one state from somewhere to somewhere, you would essentially erase that state from wherever it was before. Okay, so that's the idea. Okay, so the question is, if something falls into a black hole, and when does that information come out in the form of radiation? So that basically means that in some sense, the information that was originally there somewhere else is getting transferred into the radiation. Okay, so this is the way we would like to think about it. So this is the essential process. Okay, so this is not essential process. I mean, okay, I'll explain the process in a second. So So we want to kind of generalize this a little bit. So let's introduce what is called an auxiliary system. So this is another gimmick that people like to do in quantum information theory, which is that you introduce an extra system and you will see why. Essentially because you would like your state to be entangled with that of that system. Okay, so essentially what we are really saying is that, so all of these things are of the same dimension. I'm calling A, B, etc. just different in names, but the dimensionalities are all the same. Okay, yeah.
So by copying, you mean that you want to copy the size state in A2?
Yeah.
The state.
Yeah, essentially what that means is that all Hilbert spaces are the same, right? If you have the dimensions are the same, all Hilbert spaces are the same. So what you want to say is that there is some particular linear combination living in this Hilbert space. You are kind of want to think of, how do you move it from this substrate to this substrate, if you like. So that's roughly the idea of copying information. So yeah, so what, for instance, we'll have a scenario where there is a diary being thrown into a black hole. This is the original setup. I mean, I encourage you to read this book. It's written as almost like a, as a romance fiction almost. Okay, so it's you can go look at it. It's essentially the idea is that you throw a diary into the diary is a substrate in which quantum information is stored. You throw it into the black hole, and then it comes out in radiation. So essentially, what has happened is that the quantum information has transferred from the diary into the final radiation, and then you can extract it, etc., etc. That's the question. Okay, so yeah, so let me write that. So because it is easier to keep track of information when it is entangled with something. Okay, so we will write. So let me write it this way. So this same exact thing, once I couple it to a system C, I can write it as so let me call it 1 by D dimensionality of I. So all of these systems have the same dimensionality. Okay, all of this, A, B, C, everything. So, okay, so this is one way in which I can implement my state psi, where I view the state psi as entangled with some states is the system C. Okay, so here my so this state B is just sitting there like before here. Okay, so and this I is now entangled. This system is entangled with this. Okay, so and so the same operation I do on this guy. Okay, so same operation, same unitary that was acting on these two tensor factors. Okay, I do that, then I will basically get this guy. Okay, and D is the dimensionality of any of these guys. So that's just normalization. Okay, so so the point about doing this is that this is what one calls. So what has happened here is that what we have accomplished by doing this is that this state I is actually entangled with A at the beginning. Right? So, but when we go there, now the system is entangled, the I is entangled with B. So this is what you call, so we are transferring the purification of C from A to B. That's what this has accomplished. Okay? So that's what is accomplished here. So so in the final state, so the way you can check whether this transfer has happened is by computing this density matrix of AC in the final state. Okay, and if that is the same thing as this. Right, because this A is just sitting there. It's not doing anything. It is completely unentangled. So if you trace over B, so if you trace over B, you would get this. But if you trace over, that's basically at that point it is just this guy is just sitting there times rho of C. right? So this is how you check if you wanted to check that the structure of this thing was entangled with something else. Okay, so if you wanted to show that you have so let's say you had a system which was entangled with A in the beginning, and then you want to check whether this is now entangled with something else, then this is the way you can check it. Okay, so of course the reason why an equation like this is useful, this may seem like a completely trivial statement, but the reason why it's useful is because you can make it into an inequality. So if you remember the L1 trace norm, L1 norm or trace norm is what we always use in order to check whether the state is these two states are close to each other and no experiment can distinguish them. Okay, so if you remember the L1 norm is the one that basically has a trace of square root of m dagger m. If you have m is if you want to measure the norm of m. Okay, so trace m dagger m is what is called this. Okay, so this is what I defined. So and I said that this norm is interesting because you can show, which we don't, but you can show that if this is the case, if this happens to be the case for for a difference of two density matrices or states, any states, then you can show that that difference is so it's true for any no observation or no measurement can distinguish the states. If you bound it in the sense of trace 1 norm or L1 norm, all the measurements, all the results of measurements will be any eigenvalue that you measure would be different by this same quantity. This will be the upper bound for those guys. Okay, this serves as an upper bound for any measurement eigenvalue that you will get by measuring this or this system. Okay, and the difference in the eigenvalue. So that's why physically, so this is the physically relevant norm, and that's what we are interested in showing. So this, if we can show as a result of an experiment, after we do some operations with black holes or throwing diaries into black holes and so on, so then we can say that, okay, your information is here as opposed to there. Okay, so that's the reason why we care about these kinds of this particular structure. Okay, so so that's the sort of no. Both of these are computed here. So I am saying that if this is true, now this A is basically not entangled with anything else because you started with a state which was entangled with A, right? And in the final state, if this holds, then A is no longer entangled. So that's what we are trying to test. This is not a statement about before and after. This is a statement about the final state. Okay? So yeah. This is some unitary acting on this whole thing, right? I mean, if you have some, this is some some unitary that has support both on A and B. So the claim is that you can change states. Right? So you have some time evolution if you like. So some evolution or some process or some unitary acting on this can bring this state to this is the claim.
Sometimes two states are entangled and the third state is just a product state. So we can just switch the basis and these two are
But what do you mean by switching the basis? So here the bases are somehow held fixed. Right? The basis is basically A and B are some systems. So when I'm saying that I'm going from here to here, and in the process I want to go so that the entanglement, so the initial state, this auxiliary system C was entangled with A, but at the end I want it to be entangled with B. B.
That's what I'm saying. What is this arrow?
So this is basically a unitary acting on A and B if you like. So this, it's the same thing here. I'm, like A and B is enough to show that, and C is just sitting here. Okay. So yeah, I mean, this arrow basically means some unitary. In some, you can think of it as it doesn't even matter so much, at least at this moment, that you're thinking of as a unitary acting on the full ABC. Okay, so some unitary that does a transformation. So the claim that I was making here was that this kind of a unitary doesn't exist. That's what this means. Okay, but this kind of a unitary you can check will exist. Okay, so yeah, so this kind of a transformation. So when you say that no cloning is there is a no cloning theorem, what it means is that there is no such unitary. That's what it means. Okay, so
What is the meaning of this purification of C transform?
Purification just basically means that if you take a trace of, let's say if you forget about this guy for a second. So if you take this 0b is just sitting outside essentially, right? This is just a direct product. So this means that this whole system is entangled. Okay. So which means that if you trace over C, this A is, this is a density. Okay, maybe trace over A, this will become a density matrix for C. Right, it's not a pure state. So C by itself is not a pure state in this system. So, but the point is that this unitary, what it does is that it's, if you trace out everything, the state is still the same. Okay, but now it's purification in the sense that now the pure part of the system, or this 0b was just sitting outside as a tensor piece, but here it's no longer the case. It's 0a. So the purification of the density matrix of C here is B, and the purification of the density matrix of C here was A. So together these two guys is a pure state, and together these two guys is a pure state. Okay, so C is an entangled state. So C is, if you just look at C as a system, it's a density matrix. It's not a pure state.
Can we make A and C entangled?
What do you mean by simply entangled?
At the start, A is it's a pure state. But how did you make
You can do various things, but I'm just focusing on one particular aspect. So there is nothing, I'm just saying that I'm interested in the notion of transferring information. So that's why I'm looking at this particular thing. So you can do various things, yeah. I mean, I'm not working with some most general thing or anything like that. I'm just looking at this particular situation because something similar will happen very soon. Or more precisely, even more basically, what I'm interested in is sort of, one of the things I kind of wanted to emphasize was that if you have a piece which is, tensor factorized and not entangled, then there is a, this check is a useful thing that we can have. That's also one thing I wanted to kind of illustrate. Okay, so this is one way. So because, checking this is a non-trivial matter. Okay, but on the other hand, if you have some way of showing that this guy is much less than 1, this is actually something that you can show for generic states or some suitably generic states. Okay, so yeah. Yeah, so now the question is basically that, yes, let's say that somebody throws a diary or something containing information or a quantum computer into a black hole. Okay, so and your black holes evaporate, and we believe that they evaporate unitarily. So if that is the case, when will the information come out? This is the question. Okay, so the first thing is that if you throw a diary into a black hole, obviously because we know from Page's theorem, the information is going to be stuck inside the black hole for a very long time, right? So it'll have to evaporate till the Page time before the information will have to come out, right? So yeah, so but on the other hand, so this Hayden-Preskill observation is basically that, let's say you have a very old black hole. Old black hole means a black hole which is older than this Page time. Okay, so if that is the case and you throw something into the black hole, the information will come back very quickly. That's really the statement about the Hayden-Preskill. So let's see how that happens. So let me draw a picture like this. Okay, I'm following Harlow's picture, but kind of working with Hayden-Preskill directly, more or less. Okay, so this is, I'm throwing in a diary, and the point is that a black hole after Page time is basically entangled with early radiation. Okay, so this is my black hole, initial black hole. I'm throwing in a diary, and it comes. So the black hole is sitting here at the end, and then there is some radiation coming out, and this is some auxiliary system that the diary was initially entangled with. Okay, so and the reason why this S is useful to have is because when at some point if S becomes disentangled, which is what we'll keep track of, then you can say that the information has gone inside here. Okay, so that's the same idea there. Okay, so the point is that, so the key point, so this entanglement is just a way of bookkeeping information, but this entanglement is a fact about late black holes. Okay, so black holes are entangled. So old black holes are entangled with all the radiation that left the system. Okay, so So now what do we do? So the idea is that this U is basically a model for a black hole. Okay, so the idea is that there is some random horrendous U is a unitary operator acting on this D and B together is basically what the black hole is. So this is their assumption. So that's essentially the assumption that black hole is an extremely mixing system. Okay, so if you have a black hole, so how fast this mixing happens, etc. We kind of mentioned it last time. We expect it to be around scrambling time. Okay, so we'll say one more word about it at the end. But so that's roughly the idea. So let's say you throw something into a diary into the black hole, and everything is going to completely get mixed, and it's quantum mixing. Okay, so that means you're essentially acting on the Hilbert space with some random unitary. So that you have to understand that that's an extremely violent thing, because most systems that you have are not that mixing. I mean, they will mix, chaos, etc. exists, but here, this is, in some sense, you believe that black holes are the fastest of scramblers. Okay, so and that's why the scrambling time of black hole is kind of a bound for how fast things can mix. Okay, but anyway, so that that we'll get to eventually. But the point is that a random unitary picked from the Haar ensemble of this system, this DB system. Okay, the diary and the old black hole. So this is a combined Hilbert space, some HDB. Okay, so a random unitary picked from this Hilbert space, acting on this Hilbert space, is basically a good model for a black hole. So this is the statement. Okay, so yeah.
What is B dash and R?
So B dash is basically, so the idea is that so there will be, the black hole is emitting radiation. Right? So once you put in the diary into the black hole, it will become some new black hole B prime and some radiation that has come out. Okay? And the B prime is, you expect that as you wait longer and longer, this R will become bigger and bigger and bigger. Okay? So that's just the fact that Hawking radiation is happening and the black hole is on the decreasing half of the phase curve. Okay, so all right, so what do we check? Yeah, so the point is, so now let's so we are going to do it, let's define some sort of a reduced density matrix, which is basically the full, so this whole thing is some state, right? So this psi is basically the state of this entire SDBE system. Okay, so so that SBDE system, note, is pure because there's nothing else. It's the complete Hilbert space of everything. Okay, so and then so what this does is that so this guy, so this rho SBD is basically, you have traced out the environment, sorry, not the environment, the early radiation. Okay, and then this whole thing is being put through this U, but S is staying as it is. Right? And this D and B are evolving through this random unitary that you picked, which whatever it might be, and its dimensionality is basically dB. Right? This U is basically UdB, if you like. Okay? So that means that so rho of SB prime, let's define, so this is, you're tracing over the radiation. So SB prime is, the final state is, the final state of this piece here. Okay? So note that this E is just free flowing. It is not interacting with anything. So once you compute the trace of this guy, there's a Hilbert space that is living here. Okay, so this SB prime R. So we are tracing over the radiation to define okay, I'll explain this. So this rho SBD UBD is just a name. So this guy that I've written here, this is just a name for, I'm acting with the identity matrix on S and acting with this random unitary on the BD. Sorry. Is that fine? So what I'm doing is, so I have this rho SBD is the whole density matrix of this piece after the early radiation been traced out, and then I am evolving it. The S is not doing anything, it's just evolving by the identity matrix, but this BD part is evolving by UBD. Okay, so that's what this guy means. So, and I then plug it into this and I compute this rho SB prime. And so what am I interested in showing? So I'm interested in showing, again, the same kind of argument that we used when we were doing this page curve stuff, which is to basically integrate it over all the unitaries and then show that rho SB prime UBD, which is nothing but this guy, okay? So this is basically, so now I'm computing this SB prime, and now I am computing this norm difference that I was talking about before. Okay, so I want to compute this and I am hoping to bound it. Okay, so so like last time, I'm not going to do the unitary integrals, but they can be done, and the result I'll explain. There are some couple of things in here I have to explain. So the answer is basically that you get D by R when you do this. So this, forget about how exactly the integral is done, etc. But I just want you to understand what the ingredients are. Okay, so the ingredients are, so what have we done here? We have basically looking at this rho SB prime. Okay, so and then we are showing that this is equal to rho S times rho B prime, and rho B prime you can, because it's a black hole is of this type. Okay, so this is just the identity matrix because it's a thermal, it's a dense, it's the maximally mixed state because it's a late black hole. Okay, so I mean any for that matter. So the assumption is basically that, if you assume that the black hole is completely mixed in it all, it's in the full Hilbert space of the black hole dimensionality is B prime. Okay, so in the full this thing it is maximally mixed. That's what this means. Then this is, with this you can show that this bound comes out. Okay, and the reason why it is interesting is because that means that all the entanglement that the diary had with S is now has gone into the radiation. Okay, so yeah, so is that clear? It's clear, right? Okay, good. I was a bit worried that I have to explain it again. These things are, so yeah, so okay, so this exact same thing that I said earlier, which is that we had, if your entanglement transfers to the B system, then rho A C is equal to rho A tensor rho C. Okay, in exactly the same way, if your entanglement is in the radiation, this guy is highly bounded. Okay, and note that also this radiation is, as time goes on, this radiation is becoming, the qubits are becoming more and more. So this is a huge system eventually. Diary is presumably some finite amount. Okay, so and note that this is with each, so this is the dimensionality of the radiation that you're collecting. So which means that with each bit that the black hole is emitting, each photon that the black hole is emitting, which is essentially a qubit. So you're basically, this is falling by a fraction of half. Okay, so that means that this bound is going to get very tight very fast. Okay, so the conclusion that Hayden and Preskill drew from it is that after the page time, the information that you throw into the black hole comes out very fast. Okay, so because of the title of their papers contains the word black holes as mirrors. Black holes as mirrors. So you might think that, okay, black holes are, so the idea is that the reason why this is a dramatic thing is because a diary was thrown into the black hole so that the information will be gone forever, but instead it comes out instantaneously, the black hole is old. That's the idea. Of course, there is one more, so there are a couple of things I have to say here. One is that mirrors it seems like that information is coming out coherently. That's not quite true. Okay, photons are coming out and they contain the information, but mirrors it's more like information mirrors. It's not a reflector in the coherence sense. Okay, that's one thing. So the title is slightly misleading. And the second thing is that so even though the information comes out, it might be in some highly, it's a complicated state. It doesn't tell you that it is easy to extract that information. It only tells you that the information comes out. It's roughly again like burning piece of coal. Okay, so and that in fact is a very important fact for various purposes, that information contained in Hawking radiation is highly scrambled information. So how the quantum computation that you have to do in order to extract that information is oftentimes forbiddingly hard, and there are various bounds, etc. that we'll actually talk about it probably towards the end of this course. Yeah.
The late black hole. Is that it's like
yeah. So
the late time assumption.
it's you don't even have to make the late time assumption here. You just assume that the black hole doesn't have any information. The bound will tell you that this is anyway true. You know what I'm saying? So if yes, this is basically the assumption that the black hole is a coarse-grained density. You can make the the assumption that the black hole is the density matrix is coarse-grained. It's maximally mixed. You're making that assumption, but if you compute this, you will actually get that this is the case. Okay, and another thing I should say is that, so this is another important thing, is that in many of these, whenever you do this entangling of states like this system can be arbitrarily large compared to D. But effectively, the dimensionality that matters, because you only are interested in maximally entangling it, is that the dimensionality of this is the same thing as this. Okay, anything extra is just redundant. It's not useful for us. It's just sitting there. Okay, it's not doing any entangling work. Same thing for B and E. Okay, so the dimensionality of B is, in all these calculations, we will actually, various such replacements will happen if you look at the calculation. So this B, the absolute value of B, or the dimensionality of B is dimensionality of E, and the dimensionality of S is dimensionality of D. Okay, so these kinds of things people will use. So, but apart from that, I mean, this is, some, so again, so I will tell you, I told you this one thing that I mentioned last time, which is that this trace one norms, the way you do is there is a standard technique for doing it, which is that what you do is you square this first, you take the entire square, and then you use what is called Jensen's inequality to write this as dub with this thing square, which you can essentially like a Cauchy-Schwarz kind of replacement, and then that guy you can rewrite in terms of the L2 norm, and the L2 norms usually you can just integrate. That's the way in which people usually do. Okay, and one thing, you can look at various papers. So there is various integrals of this kind containing Uij, where these are matrices. These integrals you can explicitly compute because we know they are unitary groups. So that's the reason why these are doable. Okay, so these are things which people have done. You can look them up in. There are various recent papers where they are listed in appendices and so on. So, but the point is, these integrals are known, and so whenever you see a matrix, I'm writing the matrix indices here explicitly. Okay, so these indices are integrals on unitary groups are known. So that's the reason why this is doable, and this is the standard strategy. So you do the square, replace it using what is called Jensen's inequality, and then convert it into an L2 norm, and then explicitly do the integral. Okay, so that's what we did in the case of Page's theorem. Also, that's the same thing that one can do here as well.
So,
yeah.
So here you have written this as unitary evaluation of the trace operator, so not the density operator, right?
Correct. Yeah.
So, but usually when we write evaluation, we implement it as U inverse that operator U. Right?
What does that mean?
Usual quantum mechanics, we have some operator.
So maybe there is a dagger here. So is that what you mean? Okay, yeah, I think that dagger might have missed, but it's it's basically just a standard acting with, or unitary on the state. So if there is, you want to think of it as I think probably there is a dagger there. Yeah. So so in this, I just wanted to say that this is the evolution of this state, whatever it might be. Okay, and the point is, this object is what is going to go in here and do the integral. Yeah. So probably I think you guys know this probably better than me. Yeah. Yeah, so the information, so what it is really saying is that diary was entangled with S at the beginning, but in the end, it is entangled with R. Okay, so there is also one more slight subtlety here, which is that in showing that we have actually so you might think that, oh, the information is somehow contained in B prime times R. That's really what the diary is going into, right? But by showing that bound where row B prime is this guy, what we are really saying is that this guy doesn't contain any information. So because of which we can be sure that the information is in the radiation. Okay, so yeah, so in the quantum information language, the statement that this rho B prime is maximally mixed is in some sense the statement that it is the black hole.
So how information is coming out very fast?
So essentially because this black hole is highly entangled with this early radiation. So when you have, so the maximal entanglement is a very strict constraint. So you cannot, like that's, when you're discussing firewalls, for instance, right? We were saying that, smoothness of the horizon required the radiation, the late radiation, to be entangled with the interior of the black hole. And then we also needed it to be entangled with the early radiation because, there is no black hole left essentially at late time. So all the, entanglement has to be found between the late radiation and the early radiation. So then we argued that this cannot happen. Okay, so that's essentially the same idea. Actually, all of these are roughly the same idea. Even no cloning is in some sense a similar idea. Okay, all of them are basically saying that quantum state can only be transferred at some sense. It cannot be, it cannot be sort of redundantly copied. Let's say. I mean, it's essentially what I wrote. That's the most precise way of saying it. There is no unitary which will basically just take a state and erase the second state and replace that with the first one. There is no such unitary. So that's the statement. And roughly that's where it's coming from. The statement that B is maximally entangled with E is what is destroying it. Because if that assumption is not there, we know from Page's curve that information is you'll have to wait till page time. Right? So the system is, the radiation is entangled with the thing. So yeah, so that's, this is, it is somewhat, I think I made it more technical than what was actually necessary. So the only punchline I wanted to make was that, late time black holes they basically, if you throw something into it, it is unsurprising that information will come out very fast. You just have to remember that. That's basically the Hayden-Preskel protocol. The rest you can, it's not, you can figure it out. It's not. This integral is in some ways uglier than the Page integral also. So I think Page, if you want to remember one proof, I would recommend remembering Page's proof rather than this one. Okay? Okay, so, and in fact, Page's proof was actually proved by somebody else. It was, Page I checked it actually because last time when we were talking, I had a sudden suspicion that Page had shown some low dimensional cases and then conjectured it in general, and that was the case. And the proof was by some guy in Edinburgh. I think his name Siddhartha Sen or something. So I found that there is a proof of the actual proof of Page's theorem was by somebody else. So, but anyway, so the conjecture is what is more important. Conjecture and the realization that is important is definitely more important. Okay, so I think, so one more thing I wanted to say, that, generally speaking, I kind of wanted to emphasize the statement that, very roughly speaking, this, scrambling time, right? I just wanted to emphasize that because I don't know whether I said it last time. So scrambling time, so it shows up in this discussions of Hayden-Preskel. The reason is that the idea is that if you throw something into the black hole, how much time does it take for the diary to get fully scrambled to the black hole? Right? And that time is basically this. Okay, so this is the T scrambling, let's say. And it's a very fast time scale. Okay? Very fast means, of course, there is an RS sitting here. That means that it can be arbitrarily long time if RS is big enough. But generally, for instance, for black holes, etc., it's like a very fast time scale. It's like, I think, I still don't know what the number is, but it is, it's pretty small. It's like order of, I think it is it's less than seconds. Okay, so Yeah, so compared to the page time, which is more than the lifetime of the universe. So that's the reason why this is very fast. So, so any questions? So if you don't have any questions, I kind of want to sort of start with some motivation for holography, and then we will start with ADS-CFT, and you know, the next lecture will be on ADS-CFT, and it'll be kind of like an unfortunately a story, and story, or it's kind of like a, you know, I think it'll be, you know, you'll have to believe a lot of things, because I don't want to dwell too much on deriving ADS-CFT or any of those things. I just want to tell you a bunch of facts, like, you know, from the Mount of Sinai, so to speak, and then we want to use it quickly. Okay, so if we spend a lot of time, I don't know whether I'll be able to cover it in one day, but at least I want to cover it in 1.5 days or something like that. Okay, so today we want to make some preparation for that. So so the general story background of, you know, so string theory, ADS-CFT, etc., are what basically gave the confidence that you know, black hole information, you know, black holes are genuinely like standard unitary systems, right? So one reason was that Strominger and Waffa basically computed for certain classes of black holes. They counted the actual number of degrees of freedom living in the black hole in some indirect way, and they showed that that is basically equal to the Bekenstein-Hawking entropy. Okay, so so the thing that I will say about that is that so it is for, like, you know, it's like a highly, you know, we physicists always like to make idealizations, and the idealization that went into the computation of Strominger-Waffa, the analog of the frictionless plane, is that it's what is called a supersymmetric black hole. Okay, so supersymmetric black holes have temperature equal to 0. Okay, so and in that sense, they cannot directly tell you about information paradox in the sense of evaporating and, you know, whatever. But nonetheless, it is you know, if you can, they still can have entropy. Okay, entropy is basically related to the area of the black hole, and the question is, how would you actually compute it? You want to explain it in terms of some microscopic degrees of freedom. So the first piece of evidence, so even though it is for a t equal to 0 black hole, the fact that there is what in semi-classical gravity looks like an area has an interpretation or an explanation in terms of a state counting entropy was a big piece of evidence for believing that in string theory information is restored. Okay, so even though it is for t equal to 0. So that was the first piece of evidence. So and the second piece of evidence is ADS-CFT, which is basically this observation that quantum gravity in certain spacetimes is captured or is described by a unitary quantum field theory. Okay, so this is, you know, a specialization of that is what ADS-CFT is. So, and because of which, again, if you have black holes that evaporate, and you know, if the theory is unitary, we expect that it should be well defined even in the black hole, if you believe the duality sufficiently. So the question is whether you believe the duality sufficiently, and I think there is good reasons to believe that it is true. Okay, we'll say more about that in a bit. So, the next thing, kind of, I wanted to sort of give you a hint of is ADS-CFT is a specific realization of what is called the holographic principle. Okay, so the holographic principle is the idea that, you know, theories of gravity are very generally like this. There exists unitary descriptions in one lower dimensions of theories of gravity. Okay, so that's basically the general idea of holographic principle, and the sort of the first piece of evidence for that was this observation that let's say you form a you know, you take some object. It's a very basic observation, which is that if you form an object and let's say it has some entropy, okay, and if you contain it within you know, within the size of a black hole, let's say, so, and if this bound is not satisfied. If this bound is not satisfied, black holes cannot form by collapse. Okay, so another way of saying the same thing is that let's say you have some object of some energy or some mass m prime, okay, and it has some entropy S, and and yeah, so it has some entropy S, and let's say that, you know, if it is less than A by 4G, then, you know, it already satisfies the bound. So what you can do is you can send in a shell which, so this, okay, I mean, let me take, so let's say you have an object of mass m prime, okay, and you want to consider, so the point is that let's say you form a black hole out of it, okay, and that can essentially happen only if you have the, you know, the entropy of the final product that you have is greater than the initial entropy that you had. Okay, so for instance, when we formed it using this, what was it, this photons, this shell of photons, we observed that that entropy was A to the 3 by 4. Okay, I mean it was less than this bound. So this bound is sometimes called the holographic entropy bound. It's a very crude argument, but it's, you know, generally it is, we believe that it is true. Okay, and the reason why, the statement itself is kind of obvious from the fact that black holes form. That's really where it is coming from. So anything that, if you take enough of anything, it collapses and forms a black hole. So that's the reason why this bound we expect to be true. But the thing about this is that it is in tension with what we expect from, say, let's say, quantum field theory. So in quantum field theory, entropy is always extensive in volume. Here it is not extensive in volume, it is in area, right? So roughly speaking, the reason why quantum field theory is extensive in volume is because it's a short distance. You know, like the regularization of quantum field theory is somehow a short distance regularization. Okay, so let's say that you cut it off at some length scale L. Okay, so then the whole, you know, let me call it LP. So roughly speaking, if you take a length of size L and in 3 spatial dimensions, this is what you would expect for the number of degrees of freedom. I mean, it would scale like this, right? But that is not what happens here. So this is what is surprising about, you know, the holographic bound. And yeah, so, and I wanted to make some general, you know, this kind of motivational things that people, the reason why people thought of holography. Yeah, and another reason is that, so one of the things that we know is that, you know, so this a second reason. So the first reason is this is the reason was kind of why people really started thinking that holography is true for quantum gravity. But there was a hint that gravity might have a holographic nature already at the time when Einstein had his general theory of relativity. The reason is that, you know, we expect that metric basically fluctuates if you want to, you know, put it in a quantum mechanical system, right? So if you have, like, for instance, unlike in quantum field theory, which lives in Minkowski space is rigid and sitting there, so you can associate fields to different points. But in the case when the metric is also fluctuating, there is no background in which you are living, right? So the space-time itself, there is no, you know, there is no objective, or, you know, there is no absolute meaning to the assignment of a point, because you can, arbitrary coordinate transformations are something that you're allowed to do. So wherever, and similar thing happens, for instance, in gauge theories, which is that, you know, if you have a, let me talk about, what is a good example? Okay, let me not talk about gauge theories. Actually, so, yeah, this is, I'm a little bit disorganized because it is kind of like, you know, I'm trying to be kind of general, but at the same time, it's, so yeah, so one way to think about what is a good observable for gravity is that instead of looking at observables living in specific points in space, one natural observable is that you can integrate it over all space. Let's say something like a Riemann tensor, or, you know, many quantities. So for instance, the action of general relativity. So this, for instance, if you integrate like this over space-time, this is a diffeomorphism invariant observable. Okay, so the reason is that it's getting integrated over all space, and so, but it automatically suggests that, you know, whenever you do integrals, you have boundaries for integration. Okay, and the natural boundaries for integration over space-time is the boundaries of space-time, if it has boundaries. So that's the reason why there is some kind of a hint already, and in fact this is realized in ADS-CFT. So the observables in ADS-CFT live on the boundary of space-time. Okay, so, and so this was, you know, like if you believe that diffeomorphism invariant metric theories are the theories of gravity, and you want to quantize them, it is natural that the observables are global observables which live at the boundary of space-time. Okay, and that's one observation, but nobody took it seriously. Nobody ever took it seriously, but so the most basic things are the things which are hard to take seriously. So because this is, people always knew that there are no observables, and Bryce Devitt had papers where, in 1960s, where he observed that, the natural observables of quantum gravity are scattering amplitudes that are defined at infinity. So he could not define any observables in the bulk of space-time, okay? So, but at the same time, nobody took it very seriously. And then information paradox came along, and then this also happened. Okay, so if you are forming black holes, and black holes are, generic theories of gravity have black holes. So if you, small modification. So essentially the two defining properties of gravity are basically that it's attractive and it has black holes. That's kind of it. Okay, that's kind of the generic features. So, so if you have black holes, they satisfy this kind of an area scaling of entropy. And then you also have this feature that observables are on boundaries of regions of space-time. That's pretty good argument for thinking that maybe in a quantum theory of gravity, the observables are at the boundary. Okay, and that's what basically Toft and Susskind made into a statement called the I think Toft called it dimensional reduction, which is a very confusing word because dimensional reduction is used in every other context of various other things. So one of the great things that Susskind did was in fact to rename it into holography. So he wrote a paper 1 year later where the title was "The World as a Hologram," and I think that was but all of this was long before ADS-CFT, 93, 94. So and ADS-CFT happened 4 years later and completely independently of all of this. And in Maldasena's paper there is no reference to holography at all. Because it was a duality in string theory. That's how he discovered it. And then it was Witten who realized that this is actually a holographic duality, and a few months later. Anyway, so one more comment I'll make, kind of quasi-historical anyway, kind of this is kind of anyway next week I'm not here, so we might as well talk about random things. So one of the things, if you took the fact that observables of quantum gravity are at the boundary, one very unnatural thing you would do is to try to quantize this theory by expanding it in metric in some way, right? So, but that's what people tried for many years, including Toft. Toft is one of the first people to actually, not the first maybe, but one of the first people to really try to write down, gravity as a fluctuation around Minkowski space and then try to quantize the fluctuations. So that's one thing that people tried for a very long time. And in fact, in some sense, the culmination of that is what loop quantum gravity is. So loop quantum gravity takes basically bulk degrees of freedom, and then it tries to kind of find, tries to quantize it. But but the point is, and I think this is kind of one reason why many string theorists would think that it is a misleading, or it's not the right way to go. And the reason is that there are no local degrees of freedom. So if you really wanted to, so what holography has given us in the form of ADS-CFT is that it has somehow magically quantized gravity and told us what the answer is. So that's what holography, ADS-CFT has given us. So we were trying to quantize gravity with pitchforks and whatever, and then suddenly, magically in some particular case like ADS-CFT, you suddenly find out that okay, there is this particular theory as concrete as QCD that is the quantization of a gravity theory in some space-time. Okay, it's like as concrete. I mean, you can write down the Lagrangian, look at it, do perturbation theory, whatever you want. Okay, and that so in that sense, what it gave us is a quantization of the theory. So, but the issue then becomes, how do we get, so the reason why this whole holography is surprising is because there is local bulk physics, right? In bulk, in the gravity, we feel like there is local dynamics happens. And then the question of, when you are given like this magical entity, like, kind of a pamphlet, or, what is it called, tablet, which is, n equal for, this theory of this field theory in ADS-CFT, the question becomes, how do you get this bulk local description of gravity from it? So the problem has somehow become an inverse problem. Okay, so this is the question of bulk locality. And in fact, the information paradox is sort of the sharpest hint that we have for understanding it well. Okay, so it's kind of like, so if loop quantum gravity is basically an attempt to quantize this object and get to the holy grail of quantum gravity, So what in string theory we have is sort of the opposite problem, which is that we have a quantized, completely, battle-ready theory, which is just some quantum field theory, okay? Some quantum field theory, and it's called n equal to 4 super-Yang-Mills theory. It sounds scary, but it's like a slightly glorified version of QCD, okay? So, and for example, there are many, but that's the simplest example if you like. And in that theory, our goal is to kind of get bulk locality back. Okay? So, and I think that is enough motivation. I think I've rambled enough. So if you have any questions, you can ask. I think I'm leaving you at 5, as I promised.
So why can't we expand it around this motivation?
Because there are no local, those are not real degrees of freedom that you're quantizing, right? I mean, see, the point is that you're not quantizing genuine observables. So quantizing genuine observables are what you expect to be observed. There might be some value in it, in quantizing it in that way. It's not completely clear. But at the same time, there is also this other fact, which is that at some level you expect Einstein gravity to be sort of the lowest derivative expansion of some ultimate quantum gravity. So just taking this very seriously and quantizing it also doesn't seem like the right thing to do, because it's you can always, so the question is, you can quantize anything you want. How much do you learn is the question, right? So it's like you can quantize, phonons are a useful thing to quantize, right? If sound waves, but ultimately we don't expect that is the fundamental description of the solid, for example. It's roughly like that. So there are many indications that, including the black hole information paradox, etc., black hole, thermodynamics, etc., that general relativity has features of a thermodynamic theory. Okay, so there is, it's a bit like, So, and in that sense, it is not clear that quantizing that directly is the best way to go about it. So, any other question? This is the day for general questions. And then I think...
why is this bound basically if the entropy of some system is greater than this bound?
I didn't explain it. I have to think exactly how it comes about. But yes, I think the real answer is that... so let's say you start with an object of mass m, okay? And let's say its entropy is... what is that? What is the argument? So I think Susskind had an argument where he started with an object of mass m, and then what he does is that he collapses a shell of mass equal to the difference of the mass that you already have and the mass of the black hole that would form with that area onto that, and then that object will have a by 4gs its entropy, right? So, and then you can argue that whatever object that you already had there, if thermodynamics is preserved, it should have a lower entropy than this. So that was his argument. So right, so it's a very simple argument. Essentially, what I said is basically what it is, in the sense that, if you start with some object, you expect that the entropy, because everything collapses and forms black holes. That's really the argument. This is like a kind of a somewhat more fancy way of saying it, but it's really the same argument, which is that you start with some object and anything ultimately collapses. If you take enough of anything, it forms a black hole. So, and because of that, we expect that the final entropy that you would have, because it's thermodynamics we expect to be true, should be less than this. So that's it. Anything else? Yeah, so next lecture I think we will start with it may be a little bit fast, and I'll try to give you, you can turn that off actually. So we'll talk about ADS safety,